Classifying marine sediments. We're going to look now at how we classify marine sediments and then a little closer at the different kinds of marine sediments. Okay, particle size, location, either on the shelf or off the shelf, neritic or pelagic, and the source and chemistry, lithogenous, biogenous, hydrogenous, and cosmogenous. Particle size. So looking at the table here, we go from a class size of small, muddy, or silty, small mud size, which can be silt or clay. Sand has a variety of sizes from the smallest, very fine sand up to very coarse sand that is 2 millimeters, so a grain of sand that's pretty big. Once you get above 2 millimeters, the size goes to gravel, and that ranges from a granule to a pebble to a cobble to a boulder, like the size of your head. Moving that sediment takes energy. Over here on the right is what's called the Holstrom diagram. In the Holstrom diagram, those class sizes are here on the bottom: clay, silt, sand, gravel, pebble, cobble, boulder. On the vertical axis is the velocity of water that is needed to move that size. So the different colors here: particles eroded, particles deposited, particles transported. We're curious about this transported one here. So it takes a high velocity to move a clay here because those clay particles stick together. Then it's going to fall off a little bit here to a boulder as well. These, in this realm of sizes and velocities, the particles are deposited, and up here the particles are eroded or moved. You need that high velocity as well. Not as high for like a sand. So sand needs a less of high velocity than a clay because the clays stick together. Okay, this table 3.1 is about sinking rates. So clay, we'll just skip to it, takes a very long time for this time for a vertical fall of 4 kilometers in days. So 4 kilometers, pretty high or long, tall amount of distance vertical. 4.7 days for very fine sand, silt 470 days, but clay 47,000 days for that clay to fall through a water column 4 kilometers tall. The reason is a clay particle is shaped like a sheet of paper. It's going to just do this forever, maybe float around and then fall some more. So it takes a lot of days for that clay particle to fall to the seafloor. Okay, there's that term neritic. Neritic just means in the near shore environment over the shelf. Move my face out of the way. Neritic or near shore. The sediments in the neritic zone can accumulate pretty rapidly, coming off of this river, coming off windblown, or washing in on waves and storms. And the sediment can be coarse. That river is going to bring in some sands. The storms are going to bring in coarser sediment, or fine-grained, so mud's also carried off of that nearshore environment. There is then a slope transition zone where we get those turbidite deposits, those submarine landslides. And then out to the pelagic deposits. These are the ocean, open ocean, so beyond the rise, out on the abyss. And these sediments, we just mentioned clays, 47,000 days for them to sink to the sea floor. They accumulate very slowly, they're fine-grained, and let's look at the sources. So source classifications, are they lithogenous or terrigenous, coming from the land? Biogenous, generated by biological activity? Hydrogenous are those sediments they're going to precipitate out of seawater. Cosmogenous would be those materials that fall from outer space. So those are the sources. The chemistry of many of those sediments can be classified in two ways, either siliceous, SiO2 based, or calcareous, CaCO3 based. So calcium carbonate or a silicate. Lithogenous sediments come from the land, and they're going to be transported to the sea by wind, brought down to the sea by rivers, or even, remember ice rafting, where sediment gets trapped in an iceberg and carried out to sea. And in general, from the terrigenous environment, these sediments are going to be derived from pre-existing rocks. So imagine a rock here in the Appalachian Mountains gets weathered, eroded, those classed of pre-existing or secondary minerals get washed down rivers to the sea. Most of these sediments are going to hit that shelf and that neritic nearshore environment and stay. Some clay can be derived from the terrigenous environment. All right, so here are those terrigenous sediments near the shore environment around North America and the Middle East and into India and erosion coming off the Himalayan mountains. Pelagic sediments, I've mentioned, are going to be usually made of clay. They can be called the abyssal clays, and they cover like a carpet over the abyssal plain. The red indicates that they've been oxidized, so very slow accumulation rates, an order of millimeters of sediment over 1,000 years. They just take a really long time to fall to the sea floor. We study these sediments by taking core samples. So this is a core that was round, and it's been sawed in half and turned on its side. So two kind of moon-shaped segments of a core, and then they've laid it out in A, B, C, D, E. They're looking at the stratigraphy, or the layering within those sediments. Ice rafted debris. So here is what that looks like. The sediments are trapped in the glacier and then carried down to the coastline, and then over time this iceberg is going to melt and those sediments will fall out to the seafloor. Hydrogenous sediments, these precipitate out of seawater, so there are ions dissolved in the seawater, and they get to the point where they the concentration is high enough that the chemical reaction occurs and the compounds come together and make a solid. Examples of this could be carbonates. So I mentioned that carbonates can be biogenous, but they can also form naturally on the sea floor in these muds. Phosphorites, so these are sediments made of phosphorus. Salts, salt can come out of seawater, especially in an evaporite environment. Manganese nodules, these are manganese nodules here on the right, and they're concretions. They form around like a shell or a pebble, and then they form kind of like an everlasting gobstopper, concretions. And these are a strategic metal, meaning that the government seeks out that cobalt and those manganese nodules because they are important to our military.